Okay, well, thank you for joining us and welcome everyone to another Magnitude 10 seminar. For those of you who are not aware of what Magnitude 10 is, it's really just an opportunity for us to share information and expertise with our colleagues throughout the company. So today we are lucky enough to have Amir join us to talk more about performance-based design. Amir is an accomplished structural engineer with over 16 years experience in New Zealand and the Middle East. His primary skill set is in structural design, analysis, and forensic engineering on a wide variety of structures. Amir has a PhD in structural engineering and has contributed his technical expertise to around 20 international research papers on the topic of earthquake engineering. His professional experience while working in his native Iran include developing guidelines for seismic assessment and 5 years lecturing at a university in Iran. So Amir is committed to performance-based design, structural dynamics, and advanced numeral analysis. In addition to these specialties, Amir manages multidisciplinary teams and also enjoys collaborating with clients and contractors to achieve successful projects. So I will now pass it on over to Amir. Thank you for joining us.
Thanks, Tracy, and hello, everyone, and thank you for joining me. When I was a researcher at university, I always dreamed of bringing advanced research method into real-life practice. And soon after I started my career, I realized that I'm not alone in this dream. However, the primary challenges was the time and cost associating with testing and complex analysis, making it difficult to sell this idea to clients. But after 15 years and with the changes in the market and great support from my team here in New Zealand, I finally made this dream a reality. And today I want to share some example of how we have put this into action. But before we look at the case study, let's see what's happened or has changed in the market. So for those who are not in New Zealand, the performance of existing structure in New Zealand is evaluated using a so-called factor NBS, New Building Standard. So what is New Building Standard? We just compare the performance of existing building with the minimum code requirement for the new building. So the new building minimum code requirement in New Zealand is very similar to the US, life safety for DB level, and to some extent collapse prevention for MC level. So when we say that a building is 100% NBS, means that we can satisfy life safety for DB level. But what is unique in New Zealand is that we actually using NBS in advertising our structure, and public are very familiar with the NBS. So there's a very good example of how we're using NBS in New Zealand. There's advertising for a space in Wellington. As you can see, the space is advertised based on 100% NBS, the seismic rating, and also noted which code or guideline has been used for assessing that one. This is very unique. I'm not aware of anywhere else we have this kind of scenario. But there is a similarity between New Zealand and other locations like the US, and that's when we want to change in building use, then we need to upgrade our existing structure. So there's a compulsory, and we need to upgrade it as closely as practical to 100% NBS. It means that in ASC terminology, we need to satisfy basic performance objective for new building, or to be close as much as possible. So that's very important, especially after COVID days. Most of the office building wants to convert to residential building, means that we need to do a strengthening on those buildings, and providing a cost-effective solution for a strengthening is very important. So there's a good reason that we can promote performance-based design and those kind of complex analysis.
Yeah, I mean, at the U.S. Situation is the exact same. Essentially, the so-called conversion of it from office to existing to residential is a really big deal. And but right now, the problem is like place like LA, the cost of the conversion is a cost of a seismic piece of it that's stopping the whole programs here. So that's a big issue. Same thing
Yeah,
as
it's
I
more
guess
that,
New Zealand experience like year ago. Anyway,
yeah, absolutely. That's the same thing.
yeah.
But the other driver in the market is the new design. So if you are not aware of, in New Zealand, we just recently reviewed our national seismic hazard. And as a result, we find that the previous hazard level in New Zealand in some location was very underestimated. So in some location like Wellington, the hazard level increased by a factor of 2. Just to give you some idea what I'm talking about, this curve just showed the design spectrum for Wellington, what is already in the code, which is Wellington, that red curve, which is Wellington 1117 code, and the dashed line is the national seismic hazard. So you can see it's actually increased by almost 2, factor of 2. But if you compare that one with some area like Tokyo, the new national seismic hazard would be a lot higher than Tokyo but in other locations like Seattle and Oakland, in some range of period, we are not too far from them. And having said that, there's just soil class D, or we have higher demand for soil class C, especially for short period. That's the other driver of the in the market, because if you want to design a building based on the traditional method using shear wall, moment resisting frame, for this high level demand, then is not economically viable. As a result, you either need to use technology like viscous damper, base isolation, or try to use performance-based design to understand what's actually happening in the building and trying to optimize your design. So that is the other reason that we can promote performance-based design into the market. But do we actually have evidence for this kind of theory? This is the financial report of our firm in last 4 years. So if you see 2020, 2021, our revenue was about 5.5 mil, and we lost about $1 million. Having said that, those years was COVID years, but even before that, we had more or less similar track. We started performance-based design and promoting that to the market. Then in 2022, we were break even, and 2023, our turnover goes up to about 7.8 mil with 1 million profit. And the first quarter of 2024, we already have about 300 profit. So we can see that, or we can easily correlate our revenue to promoting performance-based design into the market.
Yeah, that's what's happening here is essentially that what you guys are providing something completely different from any other people in Wellington or anywhere. That's actually is this whole key of a talk here.
So with this kind of introduction, let's go to some case study. So the first building that I want to share with you is a building which is located in the center of Wellington. Was built in 1964-65. It's 23-story building with a 68-meter height. So this building has 7-story podium, 16-story tower, and 3-story penthouse on top. But what is unique for this building is a structural type of the building. So the original designer actually designed the building using composite component, means concrete encased steel lattice structure, or concrete encased steel profile. In the tower, the lateral resisting system is those kind of small column with a beam, so work like a tunnel system for the tower. And then those tower is supported by 16 column between the tower and podium, and the load transferred using a 2-meter deep beam on that level in terms of the transition. And again, all the columns are concrete encased lattice structure. In the podium, we also have like a cube is a shear wall, or we can call it a retaining wall as well, which is concrete encased steel structure. Because the building is actually located between two streets with a different elevation, so the designer provided opening to access a retail, but to make it symmetrical, similar kind of opening was provided at the back of the building, as you can see here, which is just facing to the dirt. So the main intention was to balance the stiffness to prevent the torsional effect in the building. And more interestingly, back in 1960, they actually did a time history analysis on this building, and they used El Centro, and they allowed for 10% damping. And that 10% damping, I think, was because of assuming some kind of ductility capacity in the system. Actually, in the recorded calculation, they said we used ductility of 2 for beams, for example, which was very interesting to me. If you want to assess this kind of building or any type of existing building, normally we use the guideline. So in New Zealand, we have NZSC guideline, which is very similar to ASC 41 guideline in the US. And that guidelines normally give us the capacity or the behavior of the component. So you have a beam or reinforced beams or column. Based on the reinforcement, based on the detailing, it gives you what is the backbone curve of those components. So we get that component level from the code and then assign it to our ETABS model or our numerical modeling to find out what is the behavior of the system. But what's happened in this building is that we actually stuck at the first step because there is no guideline, there is no code about the performance of these type of component. We don't have those kind of concrete encased lattice structure in the guideline. So the first approach that I took in my previous company was a little bit conservative approach. Let's say that we don't have a ductility on the system and we just make it work as an elastic. So what I proposed was to do base isolation in the mid-height between the top of the podium and the tower. When we developed that solution or proposed that one, we had a big challenge, and that big challenge was that because for this kind of a base isolation system, you need to provide a rattle space around the building. When we have a tower, then it's easy because the footprint of the podium is bigger and tower, then you can easily provide that rattle space. But with regards to the lift, the internal lift, for providing the rattle space around the lift means that we need to reduce the number of lifts from 3 lifts to 2 lifts, which wasn't good for converting that building to residential building. And the city council actually asked for at least 3 lifts, means that we should have added another lifts and stair from outside of the building.
Lifts are elevators for people in the US, just to let you know.
Oh yeah, sorry. So, but this actually increased the construction cost. Having said that, the risk appetite of contractor in New Zealand is quite low. And doing this kind of mid-height base isolating in the middle of the city for 23-story building is quite risky for them, which either they don't want to do that or they would charge a premium on that one. So as a result of these costs, the previous owner decided not to go ahead with this solution and sold the building to the new owner. When the new owner took the building, they came back to us and said, okay, we don't want a Rolls-Royce option. Can you propose something that is economically viable? Then we back to the first step. We said, okay, there was a big assumption at the first step that the building cannot have any nonlinearity and should stay elastic. Can we actually challenge that assumption? We try to find any code or any technical literature about the performance of these type of components. So as you know, there are codes and guidelines for composite component. We have in New Zealand, which is similar to ASCE, but most of these studies on code is about the performance of rectangular or circular concrete encased column with a steel profile. Normally, they don't talk about concrete encased steel lattice structure. And also, they're required to have a good transferring shear between the concrete and steel to be sure that they work as a composite, which we definitely don't have that kind of stuff here. There are some study about this type of component, like concrete encased steel lattice structure, but it's a little bit different in terms of the configuration of what we have here in this building. So then with this evidence, we said, okay, let's do some finite element modeling. So we jumped to Abacus and Diana to develop the finite element for the critical component, which was the column between the tower and podium, as well as beam column joint. I don't want to go to that technical detail, but if it's necessary, I can answer question at the end. But when we did develop that defined element, we find that actually the performance of component is not too bad. It seems that the column is able to take up to 2% drift. And similar to beam column joint, we find that potentially 2.5% drift they can take those kind of deformation. But as most of you guys know, with this kind of numerical modeling, you always need to have a good backup for that, because bullshit in, bullshit out. So without having a good evidence, we cannot use that for this building. With this numerical analysis, we had the confidence that by 70% chance, if we do the test, we would be able to prove that the building is ductile or have some level of ductility. So we back to the client and said, look, if you spend some money on the testing, we are confident enough that you can get a better result and we can reduce the scope of work significantly. So they believe us and they pay for test. So we did test for sample 2 beam column joint in 2 different levels, and also 2 columns between the tower and the podium, one at the perimeter and one in the corner. And the test was cyclic test. That's just a sample of the result for perimeter column and the corner column of between podium and tower. So as you can see, first of all, the hysteresis curves are very stable. So it's a good hysteresis curve. And we haven't seen any strength deterioration up to 2 to 2.5% drift, which was more or less similar to what we forecasted from our numerical modeling. So there's a big gain for us, because now we can actually have some level of ductility in the system. Even if we have a ductility of 2 in our system, we can reduce the demand by 2. So we halve the demand. That would improve the performance a lot. That's a photo at the end of the test. The performance of those columns was actually governed by the weld of those lattice structure. But as you can see, the crack happened along the height of the column, which is demonstrating why we have those kind of ductility in the system. Using this evidence with numerical analysis as a support, we actually was able to change the scope of work from mid-height base isolation to steel jacketing the column between level 6 and 8, so just 2-story steel jacketing, and put viscous damper. So we put 4 viscous damper on either side of the building, only on that level. The tower was fine, the podium was fine. It was more about the transition from the tower to the podium. So in terms of the cost saving for the client, the cost actually for mid-height base isolation was roughly about $20 million US, which dropped to about $5 million US. So it's a big save for the client. Having said that, it's not about just saving for the client. Imagine that if we just stuck with that mid-height base isolation, nothing would happen into this building. So the risk would be for public, whereas now with reducing the cost, then the clients go ahead with the strengthening, and we also reduce the risk to the public.
I think what's the interesting part of it is the using the Abacus modeling the finite element, or the doing actual testing those things, in California, anywhere, doing that for past 50 years, right? And to really understand the whole concept is that become research thing. It take year, 2, 3, 4 years to do things like the part of a PhD thesis almost. But nowadays, this technology and also the access to really cost-effective, fast lab, Amir's team has, this actually, essentially that's a huge leap here from a research kind of things to actually be able to do as a practice because of speed and the schedule and the cost. You can do that. California, if we try to do this in the private possible, or the labs, we have probably 2 years or 1 year to get to. The probably cost that $100,000 to testing like that, but they can do that in a fraction of it. I think that's a really, really important piece of it. So now our team and Amir's team can really understand here what's the realistic behavior of the structure, not only just in the computer simulation, but also the back by testing, and how we can actually do really pinpoint cost-effective solution. So the safety will be increased not only for this building, but just throughout the city, essentially now, because people can afford that. I think that's a really, really important part of it. If it's in California, we sometimes try to do more, right? The SB 1953, that's a hospital regulation kicked in almost like 40 years ago, 30 years ago, and which is seismic strengthening the hospitals for a certain level, right? But problem is it's not affordable. So therefore, they keep pushing the deadline forever, and because no one can afford it. So doing really cost-effective solution like this one is definitely be able to provide the more safety in a sense to everyone involved. Okay,
Yeah,
Amir.
absolutely right. Okay, let's
Keep
jump
going.
to the second one.
Yep.
So the second example is a heritage building, again in Wellington, was built in 1935, so it's quite old building, 100 years old building. It's a 7-story building. The lateral resisting of the system is moment resisting frame at the perimeter, and also inside says 3D moment resisting frame. So if you look at the detailing that the designer provided, it's not very bad detailing. The beams and columns is reasonable detailing. The main issue is beam column joint. There is no stirrup in the beam column joint. And also because back in 1935, they used allowable stress for designing this building. The size of the element are quite chunky. They are quite big size. When we assess the building using ASC 41 and also New Zealand code. So in ASC 41, we don't have that kind of recommendation for this kind of beam column joint when you have a reinforcement hooked into the beam column joint or hooked out. But in New Zealand, we do have that recommendation, which is from the test that has been done in 2002 and 2005 in University of Canterbury by Stefano Pampani. Based on that test, what they observed was that, these, especially round bar, would slip into the joint when you have a bending moment of the beam, which result in this kind of wedge failure. And that's very non-ductile behavior. And as a result, they said that, if you don't have a ductility in the system, you have some level of the strength in the beam column joint, but once the ductility happen, you start seeing some cracking, then that capacity reduced significantly. And in our case, we are on case 3, so even at the start it's quite small, but then you can see by a curvature ductility of 3, which is a displacement ductility of roughly 1.25, then you almost reach to 0. So that's a big issue for beam column joint, and you know that we have beam column joint everywhere. So strengthening those one is quite a big mission. And if you look at what is available in terms of the solution for strengthening, either people propose to put some hunch at that beam column joint with the intention to transfer plastic hinge away from beam column joint, or to provide a secondary load pass, make it a little bit bigger, or do this kind of FRP around the column, FRP around the beam, and trying to transfer the load or increase the capacity by tensile capacity of the FRP. But can we actually use that for this building? First of all, we are dealing with a heritage building. I don't know about the heritage rule in the US, but it's very demanding in New Zealand. So we cannot touch the outside the building. It's very
No.
limitation that.
No,
So it
it's
means that,
same. It's same here. It's same.
okay.
Very similar.
So if you cannot touch that one easily, then that hunch option or even FRP option is not anymore available or a real option. And also, if you assume that we are going to put a hunch in the interior column, means that you transfer the plastic hinge, you make your beam shorter. Now you actually dealing with a shear critical beam instead of flexure dominated beam. So yes, you solve the issue for beam column joint, but you transfer it to the beam or transfer it to the column. So it's quite tricky. Again, we started to say, okay, we need some numerical analysis to understand what's the performance of this type of joint, and is it any way that we can strengthen this beam column joint in a way that is suitable for this building. So we jumped again in Abacus and we developed the finite element model, did some kind of monotonic test and cyclic test on the Abacus and find that, okay, it seems that these beam column joint, they are not that bad. They're about 1% to 1.5% drift capacity in those joint. But now you're going against the guideline, you're going against the code. So you need to have a very good evidence why you're doing that. It's not easy that, okay, I did that numerical analysis, I disagree with the code. So you need to back up with a test. We push the button for the client to do the test. It's a full scale test and it's a bidirectional test. And one of the reasons that we did go to the full scale test was that when we look at the backup for what is in the guideline, we find that most of those tests is based on the typical detail in Europe, which they have a smaller column. So the developments of the bar into the column was quite small. Whereas for us, because they used allowable stress design and American code back then, the size of the column and beam is quite big. So potentially the performance could be a little bit different and could be actually a factor or function of the scale. We decided to go for full scale testing. So that's just a test setup and how we actually apply the loading protocol to this bidirectional test. That's quite a big mission for bidirectional testing, especially with the loading protocol. It took us about 2 days to complete just one test after setup. But what we found from the test, actually the crack happened in the beams. So that means that there is some ductility in the system. Before anything happened to the joint, the beam started to crack. But then the joint started to crack is around 1% drift. And at around 2.5% drift, that crack that you can see in the photo actually opened to about 3 millimeter. So that then that was a failure of the joint. And when we look at that hysteresis, so we find that up to 2% actually there is the capacity in the system and in the joint, and after that we can see this kind of dropping or strength and degradation. So if you look at that strength side, we find that if we use this 0.2 that code actually recommended, we get a very good result or accuracy for estimating the capacity of the joint. Whereas the code says that after having a ductility of 1.25, that 0.2 needs to go down to 0.05, so reduced by 4 times. Whereas we didn't see that kind of stuff in our test. But the more importantly is the deformation capacity. So this green line is the limit of the guideline in terms of the deformation capacity of this kind of beam column joint. This is the one that is based on one of the most recent study that said that, okay, actually the capacity is higher, which is more or less similar to what we found here in our test. And in the other direction, we actually even didn't reach to the capacity of the joint. It was 25 to 35% margin to the capacity. But then we look at why it's different. And as I said, one of the main reasons was that in the previous study, the size of the column was quite small compared to the size that we have in this building. And as you can see, the development length in their study was only 18 times the diameter of the bar, whereas in our case was 22 times the diameter of the bar. That can play a crucial role. And also in their test, all of the bar has hooked into the beam column joint, whereas in our building and in our test, half of the bar hooked in, half of them hooked out, so it distributes the load. So as a result, we actually had some ductility in the system. So you can see this previous study, there wasn't any crack in the beam and everything just concentrated in the beam column joint. Whereas for us was different. We observed crack on the beam, and also we didn't observe this kind of wedge failure. But we thought, is it any way that we can improve this beam column joint in an easy way, not using FRP or hunch? We thought, what if we go and stitch this beam column joint or reinforced beam column joint with some tiny bar? So let's go from outside that we easily have access, drill 8mm or 10mm holes, and then put 8mm bar into the joint, but diagonal bar and a horizontal bar. And actually this horizontal bond, because it's outside the building, you can bend it and you can weld it after that. So provide a good restraint for your vertical reinforcement of the column to prevent buckling if you have damage in your beam column joint. So we thought that could be an option for a strengthening, but again, there's just something that came to our mind as a solution. We need to prove that it works. So we push the button again for doing another test with this kind of solution. So as you can see, the crack on the beam distributed a lot more than what was in a main reference test. And the crack again formed in the beam column joint, but it was stable up to about 3.5% drift. And actually, even in that 3.5% drift, we stopped the whole test because there was some issue with the test setup. We were worried that it can be dangerous for progressing that test. But even up to that level, if you compare the test result with for the strengthening option with the reference option, so you can see now that the deformation capacity goes up to 3.2%. Having said that, we stop in that level. We haven't seen any strength degradation in that up to 3.2% drift. In terms of and the beam in other direction performed more or less similar to what it was in the main. And it then reached to the capacity, so no nonlinearity happened in the other direction. In terms of the strength, we didn't expect this kind of simple solution would increase the strength of the beam, the whole specimen, which that's what the test shows us. So yeah, you have 15%, but higher in one direction, but 20% lower in the other direction. That could be uncertainty on the test or different differences in the test. So that's not meaningful. It means that the strength side is more or less similar, but what we gain from that is more about the deformation capacity. So the deformation capacity on a reference test was about 2.5%. We easily go to about 3.2 or 3.5%. So it means about 30 to 50% increase in the deformation capacity. So with this kind of testing and this kind of solution, we actually was able to reduce the strengthening cost to just 500K. So imagine that if we haven't done that, our option was to put a viscous damper or to put shear wall in this building to limit the drift to less than 0.6%, be sure that the building would perform elastically and nothing happened into the beam column joint, and we provided the secondary load pass. But that's a very, very significant work because you need to put a foundation in that building. The soil wasn't great. So we're talking about something more than 10 to 20 mil strengthening costs going down to about only 500K. So that's what we added to this project. Now going to the other part of our work, which is soil structure interaction. So as you know, in terms of the soil structure interaction, we always have two options. We have one option, which is substructural option. There is a guideline. ASC give us some information about how we do that. You can model your structure in ETABS and then model the soil using dashboard or a spraying. Or you can jump to direct analysis, in which in that case, you need to model the soil as a continuum space with a boundary condition, model the structure on top, and see what's happened. And for both options, there's pros and cons. For substructure approach, it's easy, relatively easy, but the characteristic of those spring and dashboard can be a function of different parameters, can be a function of the performance of the superstructure, and is try and error. You go and change the spring, you get the pressure from the structure, and then you need to change it or update it, the characteristic. On the other hand, direct analysis, they're normally very time-consuming and very expensive exercise because you imagine that you need to model the whole soil. So there is a negative for that option, but it can capture all of those interaction, and also it can capture kinematic effect of soil structure interaction. So we thought, is there any way that we can actually solve those two main issues with direct analysis, which is time and the cost of using them? Which we did actually solve it. So one of my colleagues developed a macro that can talk and transfer or export information from ETABS to Abacus. And that's very critical for us. So the video that you are now looking at is the process that automatically our model from ETABS is converted to Abacus. And the time of converting this 9 story is exactly the same as you're watching that. So it's less than, I would say, 2 minutes. You can transfer everything from ETABS to Abacus. That's a very big gain for us because we solved that time and cost issue at this stage. And then the other issue with those direct analysis was a boundary condition, because you don't want to have a very big model. You want to minimize your model in those direct analysis to be sure that the running time is manageable. So my colleague actually bring some of the subroutine to Abacus and develop those kind of boundary condition Abacus for our modeling. So if we want to see what's the analysis process, is that we have a structure. We normally model those in ETABS, and then we use that macro that was developed and export the ETABS model into Abacus. Now is the time to verify both models. This time we cannot do the shaking table test, unfortunately, but at least we can verify one model with the other model. So the dynamic characteristic of both models should be more or less the same and should be reasonable. So the third step is that always check the dynamic characteristic, the period, the mode shape should be more or less the same. Once we ensure that the Abacus model is correct, then we push the button to run the analysis in Abacus. And also, if it's required, after finishing the run, we can bring the result into ETABS. So there's a good way of connecting Abacus and ETABS, and both parties, means structural engineer and geotech engineer, can get advantage of that. Have you used that for a building? Yes, this is a residential apartment in Wellington. There are 2 identical buildings. There are 9-story building, as you can see here. So in terms of the geometry, the width of this building is 16 meter, the height is 26 meter, and it's just founded on a shallow foundation. So 9-story building, shallow foundation with aspect ratio of about 2 in Wellington, soil class D. The first thing that everyone look at that is overturning, because it's very looks bad for overturning. So when we did use that nonlinear pushover analysis and the code-based approach, we find that the building would start to overturn, or the rock, at about 40% MBS. So the building rock, but is it end of the world if the building rocks, or is it any way that we actually can show that now we can get advantage of rocking? Rocking is not a bad mechanism if we can control it. So we said, okay, let's
So
do
guys, here the 40% MBS means the 40% building code demand. So the in the US code certain demand of a structure, and it's only 40%. Before reaching the 40% of it, it has an overturning. That's what's come from.
Thanks.
Yep.
So we jumped again into Abacus using that macro, and we developed that modeling and run a time history analysis. So you can see there's a sample of time history for one record. So you can see if you look at this corner or this corner, either corner, you can see the building started to rock, but nothing happened to the main structure. It would not result in collapse. We actually, to have a good margin for collapse, we run again for MCE level, because you need a good margin before having collapse. The other thing that we observed in this model was the ground under the building started to plastify, which actually give us a source of additional damping to the system, which normally we are not considering that in our analysis. So what we actually added value to project, our first option was to add MicroPy to prevent rocking. But around these two buildings at the back, there are new buildings that give us no access to the back of the building to install those MicroPy from outside. Means that we need to install MicroPy from inside. And as a result of that one, is a very costly exercise because of making good cost, and also it's very disruptive for the residents. So we're talking about a residential apartment. It's not easy to move everyone out once we are doing those kind of jobs. But the other interesting thing was that when you actually put pile in this building, you fix the foundation, you prevent the rocking, but you move the issue to the superstructure. So now you need to do something on the superstructure as well. Whereas if you let the building to rock, then demand on the superstructure would be a lot less and it's manageable. So again, by this kind of work and doing those numerical analysis and performance-based design, we were able to reduce the stranding costs significantly. I don't have a number to compare, but you can imagine it would be a very significant cost saving.
So this particular case, do nothing. Amir.
Yeah. Yeah.
Really interesting things of what he said is so true. You do more, especially like a foundation, do more doesn't mean it's better sometimes. This particular case actually make it worse, because if you're tied into it, it will change the completely characteristic of building, right? And also this whole structure interaction itself. So it's actually increases demand to it. So it causes the actual failure, which was not presented before you actually strengthen it. So that's actually a very important piece of it. Strengthen it doesn't mean it's always better.
Yeah, absolutely. The last example, I think I have another talk about this building, but I think it's worth to raise it again here. There's a 14-story building in Wellington Center with 58 meter, was built in 1985, designed by Holmes. The lateral resisting system of the building is moment resisting frame at the perimeter of the building, and the flooring system is a precast double T. But what is unique with this building is that is untopped precast double T. So back then, or even today, is not in New Zealand code, but in ASCE, there is some clause about on top double T, but I don't think you guys use that in a high seismic zone. Potentially in the West Coast, you're using that. To the best of my knowledge, this is one of the unique buildings in Wellington that doesn't have any topping to work as a diaphragm. So how the diaphragm force transfer, when you have one double T and the next double T, they just join this double T with this kind of connection. So you can see this is the connection that they used. So they put some kind of reinforcement at the edge of one double T and a similar reinforcement at the other edge, and then put a bar on side and weld it. First of all, the welding quality, especially when it goes to site in New Zealand, is normally very poor. Secondly, you can see there is a lever arm between this weld and this bar, result in a bending moment on the weld, which is not great. So the weld is going to fail quickly. Thirdly, when you look at what actually is on site, is very different than what they design it. So for example, here they said we have this kind of bar, another bar in the next unit, and just one bar on top weld, whereas on site they found that, okay, there is some gap between these two, let's put a plate. Who knows how they actually weld that? And it's a poor quality. So it's not a reliable connection. Definitely there is some capacity, but it's not a reliable connection on this one. So back in 2017, I guess, Becca developed a strengthening solution for this building for a previous owner. What was the solution? Okay, the diaphragm is an issue. Let's put a new diaphragm. How we are going to do that? Put a steel plate all around the building on top of the diaphragm. So a steel strap, steel plate, bolt to the concrete everywhere, with the intention of increasing the capacity of the diaphragm. So looking at that option, you can imagine that, first of all, you need to strip out the whole building to do this option. Secondly, in this building, and the services actually run on top of the floor, and then there is a false floor on top. So for doing this kind of stuff, not only you need to remove the false floor, but also remove the services to actually install this. The cost estimation for this solution back in 2017-18 was $20 million US. So the previous owner decided not to go ahead with this solution, and they just sold the building to the current owner. The current owner came to us and said, can you guys propose something better which works? I said, okay, we know that the diaphragm is weak, but in earthquake engineering is always a question between the demand and capacity. We cannot do that much in the capacity side. Let's look at the demand side. Can we reduce the demand using some kind of viscous damper or technology? I actually look at isolating the building as well, because there is a rattle space around the building, but came out as an expensive solution. So we stick with that viscous damper. But the main challenge of a viscous damper in a concrete structure is how you are going to connect that to the existing structure, especially when you have a round column. It's not very easy. You cannot easily bolt through those columns. And also the performance of this kind of viscous damper is a function of the flexibility of your connection. If you have more flexible connection, the load or the displacement is not easily transferred to viscous damper. So is not those viscous damper would not do anything. So you need to be sure that your connection is rigid enough to transfer the deformation to viscous damper. How we can do that? The only way is doing analysis, numerical analysis again, but for the connection. To be sure that the connection, first of all, has enough capacity, but also enough stiffness, is stiff enough to transfer that to the column. So that's where the finite element model helped us with this building. Also, this building was reviewed by two different engineers, Arab in Sydney and in US, and Stratex here down in Christchurch. So back in construction, the building is now in the construction. So the construction cost from 20 mil reduced significantly to 7 mil. And if you think about how we actually achieved that, in terms of the cost for the client was some cost for performing nonlinear timing instances, some cost for finite element modeling and drafting and so on, but it's nothing comparable with saving about 13 million US dollar. So I guess with that one, I want to summarize my presentation. So if you look at what capability do we have access to the lab, which is relatively cheap and is quick. As Kit said, the most important thing when you go to the lab is first the cost, but also the time. If you go to the university lab here in New Zealand, they said that we cannot do anything at least for a year. So they put you on a waiting list and we can do your test in a year time, at least. That would kill the whole project. So that's a very beneficial to us. Then we have access to numerical modeling. We have a capability of doing those kind of stuff. And also we have those kind of macro and those kind of coding that was developed here to easily convert the ETABS to Abacus and do the solid structure interaction, which get a benefit from that as well. So that's very good tool that we have. But if you look at the bigger picture from a US spec, we are very low in terms of the currency rate in New Zealand compared to US. So imagine that if you use that capability for the US market, that would be very beneficial. So if we leverage all this knowledge and experience, we actually can propose some solution which is economically viable option, and we make the building resilient. So I guess if we can do those kind of stuff, we actually reach our goal, which is to contribute to making the world a better and safer place. So with that, I would like to thank you guys and also thank my team here that helped me with everything. And if there is any question, I'm happy to take that.
I mean, I think one of the probably important thing is the to really define the clients in the writings about risk factor here, I mean, whatever we're going to do, doesn't matter finite element or the testing we're going to do, there's always uncertainty involved, if you follow the IBC here, the International Building Code, essentially the expectation is 10% probability of collapse at the MC level. Okay, so that's a code level. So if you design per code for new construction, 10% probability of collapse at the MC. And so there's the older buildings, imagine 20%, 3% probability of collapse. And however, what we're doing here is reduce that to that kind of like what you do in a code level, which means 10% of that probability of collapse. I think that's a very important communication has to make, because we're not, we're not gods. We don't know exactly what's going to happen, even at extremely refined methodology you're using there. I think that's true for any kind of seismic strengthening programs. Even new construction, I think statement of the uncertainty is very critical in a plans, by the way. That's something we have in the US, make sure that let's have that everywhere, right? Because we don't know what's going to happen, really sense. But doing this methodologies using the finite element modeling, using Abacus and Dyna, and also the solid structure interactions, and also using testing, the uncertainty is definitely much, much less than the very crude methodologies we use sometimes.
This is Ken. A quick question. I just remember from the times that I've been in New Zealand that it was always Miyamoto versus the world scene, or Miyamoto versus Holmes and Becca. And I think that Holmes and Becca were trying to position themselves in a way that they could claim to have some of the same capabilities. And I'm wondering where that is, where we are in the market over there.
Yeah, that's a good question. I actually give you more example of that fight between us and Becca. So at the moment now, Becca developed some kind of black box that no one knows what to optimize the damper. And I just look at one of their building. What I found from that document was that in the way that they are optimizing is to go with a very big damper. We're talking about 7,000 kilonewton damper, with the intention to reduce the number of damper, but then don't think about how you're going to transfer all the load to those kind of connection and those damper. And they always make a noise that no one else know those kind of stuff but us. But it's more about how to communicate with your client. And I think it's very difficult for people to question the test, because it's actually a test. How can you question that kind of test? And with those kind of testing that we have to back up our stuff, then it put us in a better position in front of those guys. And we try to educate our clients here about, like, if they're talking about optimizing the viscous damper, is not optimizing, because what they are doing, going with a bigger damper, which necessarily increase the cost of damper, is not a better solution. So with educating the client and also doing the test and being aligned with other engineers which are more or less similar opinion than us, so we were able to overcome that. So I can tell you now that in terms of the private sector in Wellington, we have more job than Becca.
Yeah, great to hear.
Yeah, I think that the way we do things like that, we're going to clean the market there as far as the performance-based engineering is concerned, as you can kind of imagine.
I do have a question. Hi,
Yes, sir.
Saul. Hello, Amir.
Hello.
Just wondering, how steep do you think the learning curve is for someone who is like to create or develop a team who is capable to run all these analyses and probably use all these tools? Like, it's not the same thing using SAP or ETABS than using Abacus or Diana, and maybe tools for post-processing. How do you think that hard is, like, based on an engineer with, I don't know, masters or something? Do you feel that it takes some time, or maybe using some tools, or what opinion do you have there, Amir?
I think it depends to what level you want to go deeply in this kind of modeling stuff, correct? For example, we have Mohammed here who developed those kind of macro for us to convert the ETABS to Abacus, and he's a master of Abacus here. So to go to that level, I would say it would take such a long time. But the other thing that we can do, we actually can have these kind of tools developed here and then share with the guys. Then in that case, I would say that it takes less time. But having said that, this kind of complex analysis is not just doing the analysis, it's more getting knowledge and experience to find if the result from the analysis makes sense or not. That's the big part of the analysis, because you can easily go and model everything in ETABS, in SAP, in Abacus, doesn't matter which software you're using. As long as you don't know what you expect to see, or you cannot judge the result, then I would say that that's less value or valuable tool. To get that experience, it takes a time. So I would say if you have a person who is good with the fundamental of nonlinearity, maybe we're talking about 3 to 4 years time to upskill them to do this kind of stuff.
Okay, well, thank you, Amir. One of the things, we really should do is any kind of work we're going to touch performance-based engineering. Let's consult Amir. Okay, I think that's a very important, and see that what he thinks and what projects can be improved, what can we done. I think it's especially at the conceptual phase, the schematic phase time, I think we should really engage them, or even before that. So that would be, I think, at the critical as working as one company, right? I think this is truly at the best practice in the world is doing in Wellington. Let's use them. Let's learn and work together with them. I think it's very important as a team. And I guess I'll say either contact him directly or contact me, and we can have discussion going for any kind of projects here. Okay.
Yeah, we are always happy to help everyone in our team, and in the globe. We are the same team.
By the way, you notice that there's the two Amirs, right? Amir Moshref, he's the Amir New Zealand, and there's obviously Amir Gilani in California, of course. So yeah, both Amirs, and they're brothers, by the way. Just kidding.
Yeah.
Anyway. Yeah, Lon.
Sorry, quick question. Can you kind of like maybe crystallize the distinction between what Amir's doing in Wellington and what we've been doing in the US with our performance-based engineering? I mean, I saw the big part of it was the testing lab access, which we're not going to do here. Generally, we're not going to do here. And I saw Abacus software, which is probably an FE platform, I imagine. I mean, can you kind of like help make it very clear what that distinction is between what we're doing and what he's doing?
I can. So basically 3 main things, right? As you said, testing piece, which we're not doing here. And the second one, using a tool which is much more refined than the ETABS or SAP or anything like that. Those are ETABS and SAP we use. There's actually the linear-based program, which tried to put some non-linearity piece to it. So there's always kind of a lot of assumptions made. But using Upcast's Dyna, it's a true finite element-based program. So that's a huge difference. Third one is the solid structure interaction piece. That is so critical, so important to really understand both the stiffness and also the energy dissipation you can get from a solid piece. That's something we don't usually model into that. Sometimes we use the local geotechnical engineer to provide us the solid springs and that spot, but they are always weird. They are always way off. Actually, that third piece is a really important one.
Is it going to be credible though to use someone from New Zealand to characterize that for design? I mean, the soil over like a local geotechnical engineer, is that going to be an impediment in the approval process?
We need to definitely have a peer review to be done. So the peer review team here will be consist of the but normal geotechnical engineer cannot do what they're doing though. So we have to select right. Most likely the professor from the university will be doing that. And we do actually identify that the professors in the US who can actually do peer review. So that would be part of a team. And things are happening like that. But I think that the most important thing is obviously what they're doing it's doing the US or Japan or anywhere for 40 years probably, right? Yeah. But that's a lab environment. That's a PhD thesis level. That takes 2-3 years. Now they're talking about you have to be able to do that in a field of essentially the typical structural engineering fee with the speed of during the design time. That's a differentiation actually.
So do you think that sorry for these kind of late questions.
No, it's good. Keep going.
Do you think that so I heard that you have developed a routine to communicate, for Abacus and ETABS to communicate with each other. Is it one way only or is it both ways?
It's both way.
Both ways. Okay. All right. So you can develop a model in ETABS and you can bring it into Abacus, do your magic, and then send it back. Okay. And then the other thing was, so if the testing is kind of an integral component of this, is it like feasible for us to have testing for a particular system in a US building done in New Zealand, like some sort of so that, I don't know if the testing is always required by what you do, because I wasn't 100% following everything you were discussing. I just saw kind of those key components that Kip mentioned. But if testing is the key component, if it is integral, if it's kind of required in order to fully leverage this, is that something that's within the realm of possibility? Or because if not, it's kind of like it takes all this off the table for us.
I think I can answer that, and then maybe Kit comment on that one. There's always the comment that we receive here as well. So first of all, to clarify that with you guys, the culture that we have here is that any job that we are doing in this level needs to have an independent peer reviewer, correct? So we always have this kind of challenge that, okay, you do the test, was the validity of the test or the value of the test, is it correct or not? So it's two things. First thing is that when we are going to do this kind of test, we normally try to have one academia as a advisor or a peer reviewer just to tick the box for us to give more confidence to the client. And also we have that finite element modeling to back up the test. So anyone who questions that kind of test, they can easily go to that numerical modeling and they can see that the result is more or less to the test. So the test is actually using to give the better calibration to numerical modeling, but it's not magic, right? So in terms of using that, I think there's no issue because we can do the test based on the material that you have, characteristic that you have in the US. You give us what do you have there. We find the closest material and we just match it and said, this is what we can do in the lab, and then provide the result for you guys.
Got it. Okay. Oh, I had one more question. Sorry. This
All right,
and you talked about you did this for that one case study. You did soil structure interaction. You used rocking, energy dissipation, all that good stuff. Is there any concern about like residual drift or residual leaning? Or is that just, you're just looking at life safety? So if there's residual, who cares type of thing?
No, actually, the rocking mechanism is actually a good mechanism because if you look at the hysteresis of the rocking mechanism, it's like a flag hysteresis. So yes, it goes to the nonlinearity, but when it back, it recenter, unless you have too much plasticity on the side.
Exactly. Yeah.
If you don't have that one, then you're fine. So that's one of the reasons that we do those kind of direct analysis. We check what kind of leaning we have. Yes, in the DBE level, we do not expect that much leaning. In the MCE level, we expect to have some level of the leaning, but who cares in that MCE level?
Okay, so that's like, yeah, CP sort of performance is what you're looking for there.
Yeah, I think
Yeah.
a really important part of it, communicate that client, right? Okay, here we done this, and we save you $10 million with no foundations, and we think this is a different way to go at the 90% confidence level, not 100% confidence level. You know what I mean? So which means that there could be potentially have the that residual, permanent, settlement could happen. So that's the business decision they have to make essentially. But we have to be, I think, clearly communicate of what we did, what we know, and we need to communicate in terms of the risk.
How do you develop a
Obviously.
confidence level like that? You say 90% confidence level. What's that based on?
I think you can do that using, in the process we're doing this, we can develop that. We can actually define it for you. Yeah, it's not a problem. Remember when you design that new construction, if an MC happens, 1 out of 10 buildings, it's collapsed. It's set in the code nowadays, by the way. Okay.
And just to add that one, when you do this kind of nonlinear time series analysis, you actually do that one for at least 11 records, correct? So you have a good database for assessing the risk based on FIMA-P 695 or some kind of guideline like that.
Yeah,
or
right.
even you can go to other guideline to find out what's the risk of collapse. So we can actually measure that.
Yeah, you can do it. You can do it definitely. What is it called? The dynamic incremental dynamic analysis to really define the probability of collapse. Yeah, we can do that during this time. All right, guys. Well, thanks so much. And Dr. Amir Moshref, thank you so much. Really appreciate it. We'll call you.
Thank you. Cheers. Thanks, guys.
Okay. Cheers. See you guys.
Cheers.
Bye.